Welcome to the first episode of Decoding AI, where we unravel the mysteries of artificial intelligence one concept at a time. Today, we are diving deep into the world of gradient boosting machines, or GBM for short. Get ready to boost your knowledge to the next level. Let's start with the basics. Imagine you're trying to make the best decision, but instead of relying on one friend's advice, you consult several, each correcting the previous one's mistakes. That, in essence, is what GBM does with algorithms. It's a machine learning technique that builds prediction models from an ensemble of weak prediction models, typically decision trees. GBM works in stages. First, it builds a model from the training data. Then, it builds additional models that corrects the errors made by previous ones. These models are added together to make the final prediction model. It's like turning up the volume on the right answers while tuning out the noise. At the heart of GBM is the loss function. This measures how far our predictions are from the actual results. GBM uses a technique called gradient descent to minimize this loss function. Imagine you're in a foggy valley and need to find the lowest point. You can't see far ahead, so you take steps downwards based on the steepest slope that you're standing on. That's gradient descent, taking steps towards a minimum error, one iteration at a time. Imagine we are real estate moguls trying to predict house prices. Each house has features like size, location, and number of bedrooms. GBM helps us combine all this information to make accurate predictions, learning from past sales data to forecast future prices. Let's roll up our sleeves and see GBM in action. We will use Python's scikit-learn library to implement a simple model that predicts house prices. Before we can predict house prices, we need data, right? Let's start by loading the California housing dataset, a classic in the world of machine learning. This dataset gives us valuable information about different districts in California, including median income, housing age, and of course, median house values. Perfect for our GBM model to learn from. With our data loaded, we can see features like mid-inc for median income, house age, rooms for average rooms per household, and more. Our target, the mid-house val, represents the median house value for each district in hundreds of thousands of dollars. This is what we will predict. Each row in our dataset represents a district in California. The features give us insight into the characteristics of these districts, while the target, the median house value, is what we will aim to predict. By feeding this data into our GBM model, we're training it to understand complex relationships between these features and house prices. Now that we have acquainted ourselves with the dataset, it's time to split it into training and testing sets. This step is crucial for a simple reason. We train our model on one portion of the data, and then we test it on a separate portion to see how well it performs. It's like studying for an exam and then actually taking the exam to see how much you've learned. We see that there's around 16,500 rows in the training dataset and around 4,000 rows in the testing dataset. With our data neatly divided, it's showtime for our gradient boosting machine. We are using scikit-learn's gradient boosting regressor to build our model. By tuning parameters like n estimators, learning rate, and max depth, we're essentially instructing our GBM on how to learn. Think of it as giving a personal trainer instructions before starting your workout regimen. Our model is trained and ready to flex its predictive muscles. Let's see how it performs on the test set, the moment of truth where we assess the accuracy of our predictions against the actual house values. This is where we see if our model can truly predict house prices or if it's back to the drawing board. The root mean square error, or RMSE, gives us a measure of how far our predictions are, on average, from the actual house values. A lower RMSE indicates a better fit to the data, meaning our model is more accurate. It's like hitting the bullseye in archery. The closer to the center, the better your shot. After putting our gradient boosting machine to the test, we have arrived at a root mean squared error, or RMSE, of 0.54. What does this number tell us? In the context of our dataset, where house values are in hundreds of thousands of dollars, an RMSE of 0.54 means our predictions are on average $54,000 away from the actual house prices. Considering the vast range of house prices in California, this level of accuracy is quite remarkable for our initial model. It showcases the power of GBM in handling complex predictive tasks. For those of you who love diving deeper or prefer reading at your own pace, we've got you covered. Check out the written blog post that complements this video for a detailed breakdown of today's topic. The link is in the description below. For the hands-on learners, there's a Google Colab notebook available as well, allowing you to run the code we discussed today and experiment with it yourself. Don't miss out on these valuable resources. If you have enjoyed our journey through gradient boosting machines and found value in our deep dive, why not show some love? Hit that like button, leave a comment with your thoughts or questions, and subscribe to the channel for more decoding AI adventures. Your support fuels our passion for demystifying AI and machine learning, one concept at a time. Until next time, keep decoding, keep learning, and keep sharing. Thanks for watching.